Thanks very much for the introduction, and thanks a lot to the organizers for inviting me. I'm really happy to be here at this conference, especially since I think I really like the topic. So hopefully my talk will have some intersection with both real and birational geometry. So today I'm going to talk about, I guess, work based on a series of projects. So two of them are joint work with Sarah Fry, Soma Shankar, Bianca Varai, and Isabel Vogt, and then another one is joint with Matty Ji. So about the color coding, so I think pink I'll try to reserve for our results, and then I'll try to be consistent with the other colors throughout the talk as well. Okay, so maybe let me just say for simplicity, we work over R, but let me say many or some results are OK over K of characteristic not equal to 2. OK. So let me start with an introduction. OK, so the motivating question is going to be if we have X a smooth projective variety over the real numbers. And so then we're going to ask when this variety is R rational. So we saw this definition earlier today and also appeared yesterday. So, or in other words, there exists a birational map from X to projective space of the same dimension defined over R. Okay, and so some necessary conditions for this, which also appeared in the talk of Andrea Finelli earlier today. So some necessary conditions. So first, X had better be C rational, because any birational isomorphism defined over R is certainly defined over any field extension. And secondly, the real locus has to be non-empty because it must contain, because I guess any open subset of AN will contain a real point. And then thirdly, as we saw earlier today, the real locus is moreover connected. So these are a few necessary conditions. And then it turns out that in low dimensions, these three green necessary conditions are sufficient. So it turns out that if dimension is at most 2, these conditions, these are sufficient to guarantee our rationality. So maybe just to briefly say why. So in dimension 1, actually conditions 1 and 2 are enough. So by 1, you can embed X as a conic inside P2. And then 2, this condition 2 implies you can project from a real point. In your conic, to get a rationality construction. And then in dimension 2, as we saw mentioned both in the talk of Olivier Wittenberg yesterday and Andrea Finelli's talk today, so these are sufficient to guarantee rationality by work of Commissati and Silhol using a classification of surfaces. And then let me just recall, as we've already seen in examples, 1 plus 2 alone are not sufficient because there's these examples of these conic bundle surfaces over P1 where basically, I guess, the signature of the quadratic form changes, and so you can get something which is disconnected, so it's irrational. Okay. Okay. So, right, so where this becomes more interesting is starting in dimension 3. So it turns out that in dimensions at least 3, these conditions above of being geometrically rational and having non-empty and connected real locus, these are not sufficient for our rationality. Or in other words, there exist irrational varieties that satisfy these conditions. So the first example that I know of is a paper of Benoit and Wittenberg, which was already mentioned earlier today and yesterday. So in this paper, they construct examples of irrational threefolds X, such that, so that's geometrically rational, the real locus is non-empty and connected, and so they exhibit a variety of obstructions. So I guess A is going to denote one example, and B is going to denote another example. So they give an example where there is an intermediate Jacobian obstruction to rationality over the real numbers, which disappears over C. And then in this example, there's no obstruction coming from unmagnified cohomology. Okay, maybe I'll call this X1. And they also give another example where there is a Brauer group obstruction, but no intermediate Jacobian obstruction. So in particular, this shows, so since the Brauer group is a stable birational invariant, this shows that for all n at least 3, you get an example in dimension n by taking the product with projective space. Okay, so these are, to my knowledge, sort of the first examples in dimension 3. And then another example I wanted to mention, which will be very relevant for the rest, for later in this talk, is there was an example of Hassett and Schinkel in 21, where they give another example where the intermediate Jacobian obstruction and the Brauer obstruction vanish, but there's a so-called an intermediate Jacobian torsor obstruction. So I'll recall some aspects of this obstruction later in the talk, but this was the refined obstruction, which was described in Olivier Wittenberg's talk yesterday. Okay, right, so the goal of writing down these various examples is just to say that in dimension 3 and higher, it's very complicated. So today we're going to be interested in studying this question for a specific class of threefolds. So specifically, these are going to be a certain class of conic bundles. So I'll define this class soon, but maybe just to give some motivation for this class. So maybe one motivation is that from the point of view of threefold classification, this class appears naturally from the MMP as one of the possible Murray fiber spaces in dimension 3. And also, this is a class that has been studied extensively over the complex numbers. Okay. Because, I mean, in order to be R rational, you certainly have to be C rational. Okay, so next I'm going to define the classes of conic bundles that we're going to be studying in this talk. Okay. So before I do that, are there any questions about the background or motivation? Okay, great. So this will be section 2. So let me write the title. So in the literature, these are known as geometrically standard and ordinary conic bundles. So for simplicity, we're going to consider conic bundles over P2 because the base must certainly be a unirational surface, and so the simplest one is to consider P2. Okay, so for the rest of the talk, we consider conic bundles X over P2 with some certain assumptions. So let me draw a picture of a conic bundle. So here's my X. It's a bundle of conics over P2. Maybe I'll call this map pi. So what this means is that all my fibers are going to be conics. So the general fiber is going to be a smooth conic, and then over some locus in the base, which I'll denote delta, there's going to be some singular conics. So we're going to add some assumptions to our conic bundles. So we're going to assume that the threefold X is smooth, and this curve delta in the base, and secondly, we're going to assume that the relative geometric Picard rank is 1. So these two together are the geometrically standard part of the assumption. And then we'll assume that this curve delta, which we'll call the discriminant curve, this is going to be smooth. So this is the ordinary part of the assumption. Okay. So furthermore, in this situation, there's another associated curve. So there's an associated curve delta tilde, which parameterizes the components of these singular fibers. So the assumptions will say that we don't get any double lines. So delta tilde is going to tell us about the geometric components of these fibers. So delta tilde is going to be the curve parameterizing this, the components. So I'll just say the geometric components of singular fibers. And so by the assumptions, this is going to be geometrically connected. So this is part of the follows from the assumptions in this setup. Okay. So these are the conic bundles that we're going to consider. And we're going to call these, okay, maybe I'll just go in this part of the board. We'll call these degree D conic bundles for brevity, where here D is going to be the degree of the discriminant curve delta. Okay. And maybe just to be a little bit more concrete over R, so what is this delta tilde? So over R, so if I have, let's say I have a point, an R point of my curve delta, then I can look at the fiber of delta tilde over this. So there's two possibilities. So either the fiber is going to have real points, or it's not going to have real points. And so in this case, there's two possibilities. So this is basically telling us which real corank 1 conic we get. So in the first case, as both of these components are going to be defined over R, and so this is going to be the fiber, this xp, so this is going to be the conic x squared minus y squared is equal to 0, so signature 1, 1, 0. And in the second case, the components are going to be complex conjugate, and just their intersection is going to be defined over R. So this is going to be x squared plus y squared equals 0. So this is going to be signature 2, 0. Okay. Yes?
Did you say that you don't have double lines as fibers?
Yes. Yeah, so that follows from the assumption that x is smooth and delta is smooth. So, yeah, so more generally, for yeah? Yeah, it's unramified. Yeah, exactly. Yeah, thanks for the question. Yeah, so if you don't require that this has smooth, then over the singularities of the curve delta, you'll get double lines. Yeah, thank you for the question. Okay, are there any other questions at this point? Okay. Okay, so right, in order to study these conic bundles over R, first we had better see when they satisfy this first condition of C rationality. So we should first see what happens over C. Okay, so this has been understood very well for a long time. And basically what happens is that the discriminant double cover, delta tilde over delta, determines the rationality of the threefold over C. So, over C, the rationality of X, maybe I'll just say degree the conic bundle as above. This is completely understood, and this is determined by the discriminant double cover, delta tilde over delta. So what happens is that if the degree is low, specifically at most 4, then the threefold is C rational. So this is due to Ivskovsky, basically by projecting from a point in P2 and getting a conic bundle surface over a function field, and then using the classification of rationality for surfaces. And on the other hand, for high degree, this threefold, this is never rational. So this was shown by Beauville, who used the intermediate Jacobian obstruction. And then maybe I'll just say for degree 5, it's a little bit more complicated, but this is determined by this double cover. So basically, if this double cover is defined by this threefold is rational if and only if the double cover is defined by an even theta characteristic. Okay, so over C, the picture is very nice, and we have a complete answer. So then what we want to do is to ask what happens over the real numbers. Again, for these classes, which we know are rational over C. So maybe we'll just consider this first class, so the class of degree at most 4. So happens over R. So only need to consider degree delta, I guess, at most 4, and degree delta equals 5 plus the even theta characteristic case. Okay. So what happens in this case is that when the discriminant has degree at least 3, if you have a rational point on your threefold, then you're rational over R. So this is not hard to show. Basically, you just have to do Ivskovsky's argument a little bit more carefully. But what happens in degree 4? Sorry? Yeah. Oh, yeah. 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 So, but I guess it's just cleaner to write the statement. Yeah, thanks for the question. Yeah. Okay. Right, so what happens in degree 4 is more subtle, and this is going to be the topic of the rest of the talk. So, right, so it's, as always, it's true that if my threefold is rational, then it must have connected and non-empty real locus. However, the reverse direction, this is not true anymore. So, okay. So this appeared implicitly in work of Hasse and Schinkel. So the example they took was if you take a complete intersection of two quadrics inside P5, and then you blow this up along a conic, so assuming it contains a conic, then they construct examples where this has non-empty connected real locus, but this is not a rational threefold. In this case, what it turns out is that if you add the stronger assumption that delta tilde, so this is the discriminant double cover curve, if this has a rational point, then it turns out that you can modify Skopsky's argument again and prove that your threefold is rational. But again, the converse doesn't hold for this statement either. So what the goal for this project was to sort of study what happens in the degree 4 case. And so let me just maybe say, so this example, this is in the more Mukai classification in family 216. So maybe one could ask, like, okay, well, why don't we study all of these? So it turns out that over the real numbers, these don't give all the degree for conic bundles over R. So to study the question, we're going to have to find a way to sort of parameterize all degree 4 conic bundles over R in some sense. Okay, right, so that's going to be the focus of the next board. So the next question is how to classify degree D conic bundles. And we're going to particularly be interested in the case of degree equals 4. Okay, right, so maybe one thing we could notice is that if you have a degree, or if you have a degree D conic bundle, so then if you take the generic fiber, this is a conic over the function field. And there's a group that classifies the conics over the function fields. So this is a Severi-Brauer variety. Over the function field. So this is a variety over the function field, which geometrically becomes a projective space, but over the ground field, it may or may not have a rational point. Okay, and there's a group which classifies these. So Severi-Brauer varieties over field K up to some notion of equivalence. So these are parameterized by the Brauer group of K. And then specifically, the conics over K, modulo isomorphism in this case, these live inside the two torsion of the Brauer group. Oh, and I just realized I didn't write the definition. So this is H2 of K with GM coefficients. Okay. So in general, this is some group, and in general, the two torsion might not give us all of the conics over this field, but certainly all of the conics over this field will live inside this group. And so then there's a useful exact sequence, which comes from Galois cohomology. So this is the purity sequence for Brauer groups. So just for our situation, you write this. So I'll write out the sequence and then sort of say what this means. So I go from the Brauer group of the function field to the Brauer group, the Brauer group of R to the Brauer group of the function field to this direct sum over codimension 1 point, where these are sort of residue maps. Okay, so what does this mean? So all the conics over this field will live inside here. So if I have a conic bundle, the data of this conic will live inside this middle part of the sequence. And then what it maps to is going to be the class of its discriminant double cover. And so under our assumptions of geometrically standard. Okay. So sort of the takeaway from this is that if x to p2 is a degree d conic bundle with discriminant curve, discriminant cover, delta tilde over delta, so then any other degree d conic bundle with discriminant double cover delta tilde over delta will be, well, I guess maybe I'll write in quotes, be of the form x eta plus alpha for some class alpha in the Brauer group of R. Right, so I think maybe something, an example which I should have written earlier. Right, so so this group for R, this is not a trivial group, but it's not very large. So over R, the Brauer group is Z mod 2, is generated by the class H of the pointless real conic. And just to give some other examples, like for example, over the complex numbers, this group is trivial because all your varieties have points. But the reason I wrote down the sequence is, so suppose I want to give all conic bundles of degree d, then for each discriminant double cover, if I find one good x, then I know that every other conic bundle, if it exists, is of the specific form, the generic fiber of my first conic bundle plus, plus this Brauer class. So it's either x eta or it's x eta plus h. So if I can find some way to give for each double cover, if I can find something in the middle, then I will get at least half of them in some sense. Yes? So, sorry, can you say, by regular classification of? Oh, okay. Yeah, this is birational over P2. Yeah, that's right. Yeah. Okay, yeah, thanks. Yeah, thank you for clarifying that. So will be, where here will be means is birationally over P2. Yeah, thanks for clarifying that. Yeah, because I guess I'm interested in rationality, so I was being a bit sloppy, but this is, yeah, right, it's only birational. Okay, so let me write down a strategy. So we're trying to deal with the case of degree 4. So the strategy that we'll use is, okay. So maybe first let me also comment. So that sequence, if I replace all the R's with C's, it's totally fine. So then what happens is the left side is 0. So in that case, the discriminant double cover really does birationally determine your conic bundle. So, but over R, we have this additional data to deal with. Let me just say strategy for degree 4 conic bundles. So, let's say fix delta tilde over delta, a natal double cover geometrically connected of a smooth plane quartic. And so there's going to be some number of steps. So step 1 is find a conic bundle y over P2 with discriminant cover delta tilde over delta. And then step 2, determine rationality of this fixed y. So then step 3, so by that exact sequence, if I have any other degree 4 conic bundle with the same discriminant, it's going to be this y plus h. So, so is this class y plus h, is this actually a conic bundle? So what I mean is this actually the class of a conic in the function field of P2 over R? So this is some sort of like period index type question. So, and then if yes, determine rationality. So here I mean like find the model over P2 and determine rationality of this model. Okay, so this is the strategy. Okay, is there? Okay, is there a question? Or, no? Okay, okay, great. Okay, so what I'm going to do, so first, before I do step 1, let me just comment that in step 2, or sorry, in step 3, this thing may or may not actually be a conic. So let me say that note so this class y eta plus h, this may or may not actually be a conic bundle over P2. Okay. Right, so to do this, let me try to give a more concrete description of one way to interpret this this class y plus h. So if I have this conic bundle y, and so if I assume that y and this class, which I'll keep writing in quotations, y eta plus h, these are both conic bundles. We can sort of interpret what this looks like by their real points. So let's say maybe like just for simplicity that the discriminant curve is an oval, like where oval is in the technical sense from Monday. So let's say this is the discriminant. So this left one is going to be y, and this is going to be this y eta plus h. So this h basically comes from evaluating a constant class of the point. So let's say if the image of the real points of y are on the outside of delta tilde, then for this other one, the image has to flip to the inside. So this is sort of a concrete way to interpret this. So let me maybe just make an observation that, so in general, for any degree D conic bundle, forgetting about this y plus h, the only place where whether or not you have real points in the fibers, this can only change along the discriminant because you're basically asking for the signature of the quadratic form to change. And furthermore, the real points of delta always have to be in the image because the fiber is either the split singular conic or this one with the conjugate components, but in either case, the singular point is going to be defined over R. Okay. Right. Okay, so going back to this, so we have sort of a picture of what it looks like to add this constant class h. And so before I do step 1, I just wanted to say that in step 3, in general, this thing may not be a conic bundle over P2. So here's a proposition. So if this delta tilde curve has a real point, then y eta plus h, this is not a conic bundle. Or another way to say this is that this class does not have index 2 in the Brauer group of the function field. So I write it as a proposition because this is actually true over other fields and without assuming anything about degree 4, but maybe over R, there's sort of a nice way to see it. So basically, so for simplicity, if I assume let's say we just have one oval in the discriminant curve, so what it means for delta tilde to have a real point is that I get this signature 110 conic as fibers. So what this means is that I'm going to have real points on both sides. Like I can't jump to signature 03 on either side. And so then in this case, if I try to sort of flip the image to be y plus h, then I sort of reverse where we get the real points. In this case, it's only going to be over this component of delta, but then above this, you're going to get something of too low dimension, because if you have a smooth threefold, then the real points had better be like a smooth three-dimensional manifold. So this is sort of a picture of this proposition over the real numbers. Okay, so in any case, this is the strategy we're going to try to employ. So again, we're interested in degree 4, so we're going to start off with an tall double cover, geometrically connected, a tall double cover of a degree 4 curve, so smooth. And so then we're going to try to employ the strategy on the top left board. So we're going to find some y, we're going to try to determine rationality y, and then we can deal with this adding the constant class. Okay, hopefully the strategy is clear. Okay, so for any such double cover of a smooth degree 4 plane curve, there exists a special threefold. Maybe I'll just say y delta tilde over delta. So this is going to be in on the classification. This is family 218. So this is a double cover. So with a specific sign choice of a 2-2 surface in P1 cross P2. And it's going to have some additional properties. So when we'll move this up, so this notation board will eventually permanently move upwards. So I can take the two projection maps, P1 and to P2. So the second projection map, pi2, this is going to be a geometrically standard and ordinary conic bundle with discriminant double cover delta tilde over delta. So this is going to recover what we wanted for step 1 of the classification, step 1 of the strategy. And we also have this first projection. So this is going to be a quadric surface fibration. And furthermore, over C, this is going to have exactly 6 singular fibers, each of which are going to be co-rank 1. So it's going to be the cone over a smooth conic. Okay, so as mentioned yesterday, so over C, this will have a section by Sen's theorem, but over the real numbers, you may or may not have a section of this. Okay. And so maybe let me just recall, so by the above, any degree 4 conic bundle is either such a y or the other conic bundle, which differs by the constant class. Okay, so this is sort of going to be how we deal with step 1. Okay. So I think we learned about this in work of Niels Gruen, but I think this is, over C, this is sort of classical and it's related to determinantal presentations of plane quartics. Okay, so I think the other input I need is going to be the topological classification of real plane quartics. So I think this is sort of very old, but I think maybe to attach some names. So I think this goes back to work of Plucker in 1839. So I think Zeuthen related it to the real bitangents of these quartics, and Klein related it to, or showed that these are in fact deformation invariant. So this gives real isotopy classification. Right, so again, this is going to be ovals in the same technical sense as on Monday. So let me just write the list and then draw pictures. So we have empty, 1 oval, 2 nested ovals, 2 non-nested ovals, 3 ovals, and 4 ovals. Okay. So the picture is empty, has no points. 1 oval looks like this, 2 ovals, 1 oval inside each other, 2 non-nested ovals look like this, 3 ovals, and 4 ovals. Okay. So this is in the same, right, so this is oval in the same technical sense as on Monday, so it cuts RP2 into a disk and a non-orientable piece. Okay. So next I'm going to state the theorem. Before I do that, are there any questions? Okay. 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 Right, so I'll state the theorem next. So just to review, so degree up to 3 is understood. So for degree 4 discriminant, we're trying to carry out the strategy on the top left. And so we have completed step 1. So now we're trying to do step 2. So for each delta tilde over delta, we found a threefold. And now we want to determine the rationality of these things. Okay. So this. So I'll write this theorem in several parts. So delta tilde over delta and y equals y delta tilde over delta as above. So these are these specific 218 guys. So for the first part, so if delta tilde has a real point, then my quadratic surface vibration has a section over R. And so as we saw yesterday, this implies that my threefold is rational over R because of the generic fiber is going to be a quadratic with a point, so you can use that to get your rationality construction. And furthermore, as we noted above in this proposition, in this case, this is the only degree 4 conic bundle. So the case where delta tilde has a real point, we are done. Okay. So the interesting part is going to be the case when this delta tilde curve does not have a real point. And so for this, we're going to have to make technical assumptions. So we have to assume that we are not in the 1 oval case. So I'll try to explain why after I state the theorem. So under these assumptions, away from the 1 oval case, we know that we show that the threefold is rational over R if and only if the quadratic surface vibration, this has a section over R, if and only if the real locus is non-empty and connected, and the intermediate Jacobian torsor obstruction, which I'll try to describe a bit later, vanishes. So this is the most general statement. So in certain isotopic classes, we have more refined classifications. For example, the full over oval one, so the maximal connected component, those turn out to always be rational. But this is the general statement that we get. And so then the second part is going to be that in part A, we need both obstructions to vanish. So by both obstructions, I mean both this topological obstruction and this intermediate Jacobian torsor obstruction. So we have examples where, so I'll just try to draw the real points of the examples. So this is, I guess, in the 2 ovals case. Oh, okay. So we have an example which has like sort of the image of the points is outside. But there's a sort of intermediate Jacobian torsor obstruction over R. So this is the picture of the image of the real points of Y. And then we also have an example where there's a topological obstruction, but there's no intermediate Jacobian torsor obstruction. Okay. So these are the first two parts of the theorem. And then the third part concerns, in this case, away from one oval, the question of sort of dealing with step 3. Can they both be rational, both Ry and this other mysterious one? Okay. So at most, one of Y or this other one, which I'll put in quotes, Y eta plus H, is rational. So I'm not making any claim about either, at least any of them being rational. I'm not making any claim about this other one even existing as a conic bundle. I'm just saying that they cannot both be conic bundle threefolds which are rational. And so maybe, okay, so why is this the case? So let me just draw a picture in the two oval, or in the, yeah, maybe I'll just do two nested ovals case. So suppose that I have a rational one. So let's say that this is the image of the real points of Y. So if this Y eta plus H, if this other one existed, then I would have to flip the points like this. But then this gives me something which is disconnected, so this cannot possibly be rational. Okay, I'm not claiming that this always exists, but if it does exist, it cannot be a threefold which is rational over R. Okay. So this is the statement of the theorem. Okay. So I think there are two questions I'd like to ask. So maybe the obvious question is we have everything except the case of one oval. So this is an open question that remains. So we have examples where the picture sort of looks like this. So we have one oval here. This threefold is connected and has real points, but there's no section of the quadric surface vibration. So in this case, rationality of Y is unknown. And maybe I'll also mention in this case, so the fibers of this quadric surface vibration, these are all empty or they're spheres. So in particular, there are no tori. So in this example, we can't apply the results of yesterday to show irrationality of this. So this is still an open question. And maybe let me just comment. So in explicit equations, we know that this Y eta plus H is rational. So we know it's a threefold and it's rational. So this is sort of a question of can they both be rational at the same time? Because in this case, unlike the other cases, like we don't have any topological obstructions to flipping the points and getting something disconnected. And another question I wanted to mention was, so it's basically true in examples that if you take the sequence of signatures of the quadric surface vibration, that in examples, this seems to determine the properties of my threefold and of my double cover. So maybe I'll just say first, this is a result due to Witt on quadratic forms. So first, so if this quadric vibration is surjective on R points, then it has a section over R. Yeah, so we actually learned about this result from the first tight approximation paper of Benoit and Wittenberg, which was mentioned in the previous talk. So this is a result about sort of quadratic forms over function fields of real curves. And so another question is, so if pi1 has no section over R, then do the signatures of the fibers of the quadratic surface bundle determine properties of y and delta. So specifically in the examples, it seems that this determines like the isotopy type of delta, and so maybe this is a sub-question of is rationality in this family, at least if we remove the locus of singular quartics, a real isotopy invariant. But of course, to answer this question, you would have to answer the first question first. Okay, so I think I'm out of time, and I think then I did not talk about the proof, but I'm very happy to discuss the proof with anybody if they're interested. So I think this has been 50 minutes? Yep, okay. So thanks very much for your attention.